Okay, let's consider mappings. So mappings are very similar to functions that you've met, and you'll see how we define functions specifically later on. So we have several different types of mapping here, and we're going to have so if we take this one as our first example, in this mapping we'll just quickly sketch a graph of what it looks like. So quadratic, you could factorise that and see that the roots are at 2 and 1. We can see that for any given input, any given x value, I know exactly what y value I'm going to get out. So that means that we have a function here. Anytime where you know the output for a given input, you have a function. However, we also notice that for this given output, there were 2 possible inputs. And we can see that's true for most of the values here. For any given y value, any given output, I could have chosen at least 2, any one of 2 inputs. So this is what we call a many-to-one. For any given input, I know the output, so I know it maps to 1, but many x values can map to one y value. Sometimes that's represented with this kind of sketch. So you've got your x's here, your outputs there, and then many x values can map to one y value. They may only map to 1, like the minimum point on that graph only maps to one y value, but the key is many x values can map to one output. Okay, so that's what we call a many-to-one, and it is a function. As long as we know where each one of these lines heads, we've got ourselves a function. Okay, let's consider this one. So again, we'll start off with a quick sketch of what it looks like. Something like that. Here, we can see that for any given input again, I know what my output is. So this is again definitely a function. Okay, as long as if I know the input, I know the output, we have ourselves a function. But this time, if I know the output, I can see that there was only one input that I could have had. Yeah, if I choose down here, again, it might be very, very close to an asymptote, but it will never take that value again. It will always be slightly below that point. So in this case, for each input, I went to exactly one output, and I could reverse that process. I had a 1-to-1. That means that for any input, I get exactly one output. Okay, 1-to-1. Every input goes to one output, and every output came from one input. This is also a function. Now let's look at this. So this is the inverse of some sort of quadratic. So it's saying that I've got plus or minus the square root of x plus 2. So our graph will look something like that. But importantly here, I've got a plus or minus. So for every single input, I can work out 2 possible outputs. So if I put in x is 1, that could have gone to 2 possible values. Plus root 3 or minus root 3. I don't know which, or I could choose which. So we can see, again in this little diagram here, one input can have many output values. It may only have one, as in that point just there, but in general they could have 2 or more outputs. So this kind of function, this kind of mapping, this is not a function because I don't know the output for a given input. We would say is a one to many. Okay, just looking at that graph again. One input goes to many outputs, but if I know the output, I know exactly what input I put in. So many of these will map to just one of those. Okay? And then finally we've got a different kind of mapping again here. So in this case, this will be a little bit more complicated. This one's actually going to look like a circle. Sorry, that should have been written like this. That's going to look like a circle. And now we reach the many-to-many case. If I have an input, that could have gone to many outputs. Again, remembering that many means two or more. But also, that output could have come from many different inputs. So in this case, we have a many-to-many mapping. Many inputs go to many outputs, and vice versa. Okay, again, there are some points where it could be unique in one direction or the other, not in this case, but in another example it could be. But the key is you can have that splitting, heading in either direction. Okay, so in this case, if we don't know our output, if we know our input, we don't necessarily know our output. And also if we know the output, we don't necessarily know what the input was. So only these two are functions. For it to be a function, I must know the output for a given input. That process doesn't need to be reversible. Okay, so we're going to concentrate on these. We'll ignore those for now. So if we have an inverse function, that's a function which takes us back to our original input. If we look at this case, for a given input, I knew the output. However, if I try to reverse that process, if I start off with an output and try to figure out my input, I can't do it. I'd have to guess at this point which one my original input was. So as I flip this round and I try to run the process backwards, this would become a one to many again. Okay, if I tried to reverse this process, head the other way to find f inverse, that would become a one to many. So this would not be a function anymore. F is a function, that's well defined. However, f inverse is not a function. The inverse function of a parabola does not exist, because if I take the inverse of that, which would be reflect in the line y equals x, we'll see why that works another time, and I reflect it in that line, you can see that now if I know the output of the original function, or the input of my inverse, it can go to two different values. Okay, so that inverse is not a function. For an inverse function to exist, I will need a one-to-one mapping. If we look at this scenario, for a given input, I know the output. And I can reverse that process. If I know the output, I know exactly which input I'm going to. So again, if we look at the original graph of this, and then we sketch the inverse. So again, reflecting in the line. something like that. No, it's not. Terrible sketch. Reflecting in the line, that will be like that. Terrible first attempt. I can see that again, for a known input, I definitely know the output. So if I know what the original output of my function was, I can reverse that process and find the original input. And that's the idea of when an inverse function will exist. So an inverse function only exists if our mapping is 1-to-1. If and only if the mapping is 1-to-1. Okay. Because for it to be a function, for any given input, I must know the output. And for the inverse to also be a function, I must be able to reverse that process.